A solid ball of radius 5 centimeters rolls on the inside of a track of radius 1 meter. If the ball starts from rest at the vertical edge of the track, what will be its speed when it reaches the lowest point of the track, rolling without slipping? So this is a typical rolling without slipping problem, and we want to know the speed of an object at the bottom of some ramp or hill or track. Now, since we want v, you might think that we would use kinematic equations. The problem is most of those either use time or assume that the acceleration is constant, and here the acceleration is definitely not constant. What we can do, though, is apply a concept of conservation of energy. We only have the force of gravity to worry about, the normal force being applied from the track, which doesn't do any work. There is friction, we assume static friction to make sure that the ball can roll, but static friction is not a resistive force, so that is okay. So the main concept that we want to apply here is conservation of energy. And the equation for that looks like this. Initial energy is equal to final energy. We're always talking about mechanical energy here. Okay. We also do have free rolling, which provides a simple relationship between the translational speed of an object and its rotational speed. So let's list some other equations we might need. The initial and final mechanical energies are equal. What we'll need is the reminder that the energy, the mechanical energy, is equal to a translational kinetic energy plus a rotational kinetic energy plus whatever potential energy we have, which I'll write as capital U. In this particular case, the only kind of potential energy we have is that of gravitational, so I'll put a subscript G. The translational kinetic energy is given by 1/2 times the mass of the object times its center of mass speed squared. We have a rotational kinetic energy as well, 1/2 times the moment of inertia times omega squared, the angular speed squared. And then finally, the gravitational potential is given by the mass of the object times g times whatever its altitude or elevation is. And we can always decide to put 0, y equals 0, wherever we want. Okay, what else do we have to worry about here? I suppose we can now apply conservation of energy and see if we can make some progress. The initial and final energies are supposed to be equal. Let's make a list then. The initial energy. Well, the initial kinetic energy is 0. So the translational and the rotational kinetic energies are 0. But we do start off at some particular height. So I want to put m times g times the initial height. And here's where I need to be careful. Where do I want to put my 0? If we want to track the motion of the center of mass of the ball, then I'll put a dot here. And I'll let the bottom be a position of 0. So let's let this be 0. Now what that means is that the initial position of the center of mass is up here. Notice it is not at a height of r above 0, because by that I mean capital R, the radius of the ball is little r, but the radius of this half circle is capital R. The difference between them is what we need. In other words, the initial position of this ball, as referenced from the bottom, is at a height of big R minus little r. So that is the initial y position that I need to put in. Okay. I could have put 0 at the bottom where the ball touches the track, but we would have gotten the same answer. The final energy here, there is translational and rotational kinetic energy, 1/2 m center mass speed squared plus 1/2 I omega squared plus mg, the final y position, as we said, was 0. And so there we go. We can now set these things equal. So let's do that. We're now applying conservation of energy. That tells us that we have mg, big R minus little r, is equal to 1/2 little m center of mass speed squared plus 1/2 I omega squared. Okay, that is equation that I'll call number 1. We can also apply a relationship between the center of mass speed of the ball and its rotational speed, because we have this condition of rolling without slipping, also known as free rolling. So the free rolling condition looks like this. Center of mass speed is equal to, so in fact, think of it this way, it's proportional to the angular speed of the object, and the proportionality constant is the radius, assuming it's a round object. We'll call that equation number 2. And then finally, something that you can always look up or compute with calculus is that the sphere has a moment of inertia. The moment of inertia of a sphere, in particular a solid sphere, is given by 2/5 times the mass of that sphere times its radius squared. And at this point, I can see that there's already a mistake. We have to be very careful. The radius that goes into the relationship between speed and angular speed is given by the radius of that object. Remember, the ball has a radius that we're calling little r. That is the radius that needs to go into this formula. The same is true for the moment of inertia. It's a sphere. The formula, we're told, is 2/5 times its mass times its radius squared. Its radius is little r squared. One has to be very careful in problems like this. Let's call that equation 3. We have essentially done all the physics that we need to. The rest of the problem is mathematics. So here are our 3 equations. What we can do is take equation 2 and solve for omega. Let's solve for omega in this way. And what we'll do now is apply this to equation 1 along with equation 3. So we'll put this all into one master equation. What we end up with is mg big R minus little r equal to 1/2 m VCM squared plus 1/2 the moment of inertia of the sphere is itself 2/5 mr squared, and then the angular speed squared, which is center of mass speed over r squared. It looks like a lot, but with some algebra we'll see that this cleans up nicely. Notice what happens. A 2 cancels a 2, the r squared cancels the r squared, and what we end up with here is 1/2 m VCM squared, that's the translational kinetic energy, plus a 1/5 m VCM squared. So there's rotational kinetic energy there in that last term. At this point, you'll notice that the actual mass of the sphere is irrelevant in terms of, for finding the answer to this question. The mass appears on both sides of the equation in all terms. We can divide. Combine 1/2 and 1/5 to give you 7/10, and then we can rearrange and solve for the speed of the center of mass. 10/7 g capital R minus little r equal to the center of mass speed squared, so we'll take a square root, and that's the algebraic expression that we wanted. Now we should do a sanity check to see if this makes sense. The sanity check. What happens when little r gets so big that it is equal to the radius of this track? So when little r becomes big R, then what we have is the center of mass speed goes to 0. Does that make sense? Well, think about this. What we're saying is if the sphere has a radius that approaches the radius of the track, then basically it starts and ends in the same position. And so naturally, if it started at rest, it's going to end at rest. So that makes sense. Notice what happens when little r goes to 0. The expression VCM goes to square root 10/7 GR. So it still has this funny factor of square root 10/7. You might wonder about that and you worry that you've made a mistake. But there's no mistake here. The thing that we have to keep in mind is that what we just learned was the rotational kinetic energy is itself 1/5 VCM squared, and that ultimately is where we can understand why the speed of the sphere at the bottom will give us some funny factor with square roots of 10 and 7, because we always have this no matter what. We have even if the radius of the sphere goes to 0. Okay. Finally, let's take our final result and plug in the numbers that we have. We have a square root 10 over 7. G is 9.8 meters per second squared. Big R is 1 meter. Little r is 5 centimeters or 0.05 meters. When you work this out, you'll find that the answer is 3.6 meters per second. And just as a sanity check, you'll notice that if we were just to have computed square root 10 over 7 GR, that would give us 3.7 meters per second. And so our answer is slightly different because the little radius of the ball makes it so that it doesn't drop down a full radius of a track.